Yeah, we now turn to chapter 12, which is about linear regression and correlation. And to give you an insight of what this is all about, consider this example here about scuba divers. So scuba divers have a maximum dive times. I mean, they have maximum dive times they cannot exceed when going to different depths. So in other words, the time that you have to stay under the water is limited depending on the depth that you have gone down. So what I'm saying here is that we have what we call bivariate data. This is what we call bivariate. Bi means where you are given a data set with the two values describing each unit. So if you dive 50 feet down, you can't exceed 80 minutes doing so. If you go down 60 feet, the time comes down to 55. If you go down 60 feet, the time comes down 55 minutes and so on as you go deeper. If you go down 100 feet, you should not exceed 22 minutes. So this is what we call bivariate data. And there are so many situations where we have bivariate data. You have two values that describe as kind of a situation. And from this bivariate data, you may be interested in answering a bunch of questions. Number one, is there a linear correlation between X and Y? What does that mean? If we call this X and we call this Y, if the depth is the X and the time is Y, can we create a mathematical equation which describes the two variables in a linear fashion? That's the question. And many of you have done some algebra before. Have you heard about this thing here, y equal to mx plus b? I'm sure I've seen this before. Okay, whereby the two variables y and x are described in the linear fashion, meaning that if you plot this point, this is x and y, you kind of come up with a straight line. Is that the case for these two variables? You know why? If the answer is true, then you open up a bunch of options for using this data. Number one, you can predict. Can you predict the time when x is 75? And look at the x values we have. We have 50, we have 60, we have 70, 80, 90, and 100. 75 is missing. What is the maximum dive time when x is 75 feet? So if you have this equation, the answer is yes. You can predict the maximum dive time if you go down 75 feet. And you know what? Because the x value we are using is inside the range of values, the range of values for x are from 50 to 100, and 75 happens to be inside somewhere. We call it interpolation. So can we interpolate? Maybe, maybe not. But this comes from the fact that you can have a linear equation anyways. So if that's the case, can we do interpolation? The answer is yes. Look at number 3. Can we predict the time when x is 105? Now 105 happens to be outside the range of the data set for x. We call it extrapolation because you're going beyond what you've been given. And turns out that anytime you have bivariate data, extrapolation is not encouraged. Yes, because 105 is way beyond the limits of our domain, as they call it. Extrapolation can be done, but it is not encouraged. If this was 101 or very close to 100, that would be okay, maybe 100.5. But if you go to 105, we discourage extrapolation because the data could have changed. The linearity, if any, between x and y could have changed. So in this chapter, we're talking about having bivariate data, and we kind of change it using algebra in a way to try and answer a bunch of questions. And that's what we call, linear correlation and regression. So the first thing to do anytime you have bivariate data is to start with something they call a scatter plot. Yeah, a scatter plot. So in other words, you plot. We know what plotting is, right? This is the X variable, this is the Y variable. And so it's like this first observation here yields an ordered pair called 50, 80. This ordered pair is going to be 100, 22. So you plot those points on the XY coordinate system. And the reason they call it a scatter plot is that you may end up with points which are scattered like that, maybe. So you always start with a scatter plot. And this scatter plot is what tells you whether or not you are able to answer questions of this nature. Okay? So like if I look at this example here, I have X and Y. The X is like there, and the Y is the number of users of, I think, MCommerce in millions of people. You know, so regardless, we have already pairs. So 2000, 0.5 is right down here. 2220 is right down there. 2333 is up there, and 2447. So this is what we call scatter plot. And the way the scatter plot looks, the structure or the image that you get from the scatter plot is what tells you whether it is well worth pursuing a linear relationship or not. You know why? Because let me just run a little bit here. Because sometimes you may end up with scatter plots. For example, this one, that one, this one, and then the others right here. So the pattern of the dots is what tells you whether or not there indeed is a linear connection between the two variables. Let me start with this one here on the right, which I'm trying to hover over. If the scatter plot really looks like this is like a cloud, you cannot hypothesize about the possibility of a linear connection. If the pattern looks like this looks more like exponential, because a linear pattern means a straight line. You know, I can have a pattern which looks like this, which looks very good. As you can see, the points are really climbing up. I may have a pattern which looks like this. By the way, when the pattern of the scatter plot goes up, we claim that we have a positive linear pattern. And the strength, as they call it, the strength of the linearity depends on how close the points are to a straight line. If, you know, there are like this other scatter plot here, there's another point which is up here. That is, we can call it linear pattern with some kind of a deviation in one of the points. When the points come down as you progress from left to right, we call it a negative linear pattern. So this is a very strong negative linear pattern. But this is also a linear pattern, negative linear pattern, which is weak because the points are not so close to being on a straight line. So the scatter plot is always the starting point. Now let me go back a little bit and I explain to you a bunch of other things as we move on. Okay, now when you have the variables X and Y, if I go back to my first example, we know that in order to find Y, we must find X first. So Y depends on X. It is after you know X that you can know Y. In that regard, X is called the independent variable. X is called the independent variable. There are so many names. We can also call it the explanatory variable, or we can call it the predictor. In fact, predictor makes more sense because you can predict the Y values if you know the X values. On the other hand, the Y values are also, the Y variable is also called the dependent variable because it depends on X. In so many books, they call it the response variable because it responds to the X variable. So let me Look at this example here. Amelia plays basketball for her high school. She wants to improve to play at the college level. She notices that the number of points she scores in a game goes up in response to the number of hours she practices her jump shot each week, and she records the following data. 5 hours, 15 points. If she practices for 7 hours, on average, she scores 22 points per game. When she practices for 12 hours, half a day, she's expected to, when she recorded, she made 36 points. So you can see that as the number of hours increases, so the number of points scored in a game. Construct a scatter plot. Well, we are going to see how to do that with using technology. Matter of fact, the calculator that we're going to use is going to give us everything that we need on one screen. You're going to see the scatter plot. You're going to see the many other things as we shall move on. But in any case, we have the x variable, y variable. You want to make sure that x is the x variable. When the machine asks you to put in the independent variable, they are talking about the x variable because the y variable depends on the x variable. Okay, these were some of the instructions if you're using a TI-84, but let me pass on that because we have another calculator. A scatter plot shows the direction of a relationship between the variables. A clear direction happens when there is either the two situations, high values of one variable occurring high values of the other variable, or low values of one variable occurring with the low values of the other variable. Like this guy here, like this scatter plot on the left, which I labeled 1. You may also have high values of one variable occurring with low values of the other variable. In other words, maybe as the x increases, the y values go down, So this second type here. You can determine the strength. You can determine the strength of the relationship by looking at the scatter plot and seeing how close the points are to a straight line. In this case, we're going to look at linear correlation. We should not worry about the power functions or the exponential function. But if you are investigating power functions, exponential functions, or some other functions, then the scatter plot really tells you what is going on. In our case, for a linear relationship, there is an exception. You can see the scatter plot where all the points fall either on a horizontal line or vertical line or whatever it is. All right. When you look at the scatter plot, you want to notice the overall pattern and any deviations from the pattern. Okay. So like these examples I was talking about, this is a positive linear pattern. This is a positive linear pattern with the one deviation because this point up here is a little bit off from the rest. This is a negative linear pattern, which is very strong because the points are very, very close to fitting on a straight line. By the way, many people believe, I don't know why, when we talk of a straight line, the straight line can be anywhere. It doesn't have to be horizontal only or vertical. A straight line can either be going up or going down. So a straight line doesn't mean one which is horizontal only, as many people kind of purport it to be. This other guy here is a negative linear pattern, which is weak. This is not a linear pattern by any stretch of imagination. And in fact, there is just no pattern. So before you do any mathematical computations, I'm saying the scatter plot should be the starting point. If I had my scatter plot that looks like this, I forget about linearity and maybe think of something else. So it is like the gate, which gives you the go-ahead to continue or even to stop right there, the scatter plot. Once you have a scatter plot, let me go back to my here. Like the first question I had here, right? Is there a linear correlation between X and Y? If there's a linear correlation, we can create an equation. That equation is what we call the linear regression equation. call it the regression equation. By the way, data rarely fits a straight line perfectly. Usually you must be satisfied with rough predictions. Typically, you have a set of data whose scatter plot fit, in quotations, a straight line. And that line is called a line of best fit, or a least squares line. Okay, so basically here's what happens. Let me just walk you through what really happens here. Imagine if I had, forget about the blue line here. Imagine if I had, forget about the green line. Is it green? Look at this, my scatter plot, right? They are not fitting on a straight line by, completely, but you can construct what we call a line of best fit. Like, look at that green line, but I can also draw a line like this. By the way, I can also draw a line like this. I can, it's like when there's a hurricane, the models that they use to tell us where the location, the path of the hurricane is going to be. So basically, there are so many possibilities. There are so many possible paths you can use. Question, which one are we going to use, given that there are so many possibilities? And here is the thing. For each of the possibilities, like I have now the green line and these other two lines here, you look at the deviations, how far each point is from the line. Now let me first remove this. Look at the green line that I have here. Imagine if I have this line here, right? For each point, like this point right here, you determine how far off this gap from the line to the point, and this gap here from the line to the point, this gap, that gap, all the points, right? So you determine the so-called deviation of the point from the line. And because some points are below while others are up, you square those deviations and you add them together. So you add the square of the deviations of each point from the line. Then you look at another line and do the same thing. Sum up the square of the deviations of the points from the line. The vertical distances, those can be measured. And if you're gonna do it for all the possible lines, okay, you would like to pick the line which minimizes the square of those deviations. That's why we call it a least squares line. The good thing is that the calculators have an algorithm that will do this thing for us automatically. But in any case, it can be done using pen and paper. Let me repeat, after having the scatter plot, because there are so many possibilities of the line that can be concocted through those points, you select the line that minimizes the square of the deviations, the square of the sum of the gaps, if you will. The gap, how far each point is from the line, how far each point is from the line. You square those gaps and you sum them together and you select the line that has the least sum of those squares, and that's why we call it the least squares line. And once you have that line will be always in the form y is equal to mx plus b, and we know what m is, what m and b are, but in any case, if you've done algebra before, m is the slope of the line, b is the y-intercept, which have a lot of practical meanings in the context of the problem. And once you have that line, pretty much everything is gonna be okay. The process of it, the best line is called linear regression. The idea behind finding the best line is based on assumption that the data are scattered in a straight line. The criteria for the best line is the sum of the squared errors or deviations is minimized. Any other line you might choose would have a higher sum of squared deviations, and so that line is called the least squares regression line. Now, using calculus, you can determine these values A and B that make this thing a minimum, but you still have a calculator. When you make, so when you do that, this is the line that you end up with. Y hat, we use Y hat because this is the equation itself. This is the line itself, because these are like the predicted values. You are saying these are the predicted values which look like this: a plus bx. Now, sometimes you'll see y hat equal to ax plus b. It does not matter. The thing here is the value before x is the slope. If the calculator gives you the format of equation to be this one here, and they ask for the slope, the slope is the number which is before x. If the format is of this nature here, the slope is b, but it doesn't matter. And a in this case becomes the y-intercept, b becomes the y-intercept if the equation is in this format. So it really doesn't matter. I know we're used to this y equal to mx plus b, which is of this nature, but I'm saying it is also possible to have the equation of the line to look like this other box here. All right. So like I said here, for such a line, the slope is b, and the slope has a lot of meaning. What does the slope mean? The slope is the rate of change. So here's what it means. It means that for every unit increase in x, whatever x is representing, if x is the number of hours Amelia practices her jump shot, okay, then the meaning of the slope tells you that for every unit increase in x, the y values increase or decrease by b. Why do I put increase or decrease? Because this b could be positive or that b could be negative. So that's a big deal. You are now saying that on average, the y values increase or decrease by that much. Anytime you increase the unit, the x variable by 1. So wherever you are, if you increase x by 1 unit, you expect the y values to change that much. And this guy, the number which is not with x, is called the y-intercept. So in other words, just to put you back in business, if this is my x and y coordinate system, and the line is going to do this, maybe this value here is the y-intercept, the point at which the line intercepts the y-axis. Now, by the way, this y-intercept may or may not have a meaning in the context of the problem, but the slope always has a meaning. We shall see some cases. The slope must be understood. In fact, I talked about it already. Okay, how do you interpret the slope? The slope of the line tells how the dependent y variable changes for every unit increase in the independent variable. So like again, if I go back to Amelia, x was the number of hours she used to practice her jump shot. Y was the number of points, okay? Suppose the slope is 8. Then what's the meaning of that slope? You would be saying that for each extra hour she practices her jump shot, the points are expected to increase by 8. Yeah, that is the meaning of the slope. And it really has a lot of meaning in the context of the problem. All right. A random sample of 11 statistics students produced the following data, where X is the third exam score out of 80 and Y is the final exam score out of 200. Can you predict the final exam score of a random student if you know the third exam score? So in other words, the teacher gave them exams, but he is using or she's using the score on the third exam to predict the score on the final examination. So it appears that this third exam is very huge because it has maybe a lot of stuff connected with the final examination. So a student who scored 65 made 175, one who scored 67 made 133, etc., all the way. So maybe this is for this semester, and he wants to see whether he can predict for the next semester's performance based on the third exam. So how do we start? Here is a scatter plot. We're going to see how to do that on the calculator. And then once you do that, the onus is on you to find this, the straight line or the regression line. And so on, as you can see, the third exam is always the horizontal axis is always X, the vertical axis is always Y, but I'm putting the actual definition of what X is, the third exam score and the final exam score on the Y axis as well. Okay. And then you take it from there to find the linear regression equation. So let me go and bring up a calculator online and I show you how to go about it to create that scatter plot and whatever comes up with it. All right. So chapter 12, let me go for linear regression here. And again, like the rest of the assignments, the very, very first question here populates for you a linear regression calculator. There it is. So let me check it out now and let's see what we have. All right. Now, ignore, let me see, yeah. So here it says that enter data separated by spaces or commas as 2 rows or 2 columns. So it doesn't matter. As long as you have 2 rows or 2 columns, you can do your thing. It is possible to paste, copy and paste. Unfortunately, this is not text data here that I have on my screen, but in your homework, I will show you, you can copy the data and paste it in this area here. So let me just type it, 67, 175. Oh, no, 65, this was just, then 67, 133. Okay, then we have 71, 185, 71, 163, 66, 126, 75, 198, 67, 153, 70, 163, 71, 159, 69, 151, and another 69, 159. How many are there? Let's check it out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I think we are good. So this is what you do to enter your data. And ignore all this stuff for now. We're going to check it out later. But when I say calculate, select on, okay, all right, let me just go ahead and do that. Then when I say calculate, as you can see down here, okay, this is our line here. So it created a scale for us. Okay, we have the X down here. We also have the Y axis over here. And, you know, we have the scatter plot right here. And in fact, the straight line kind of almost went straight through the points themselves. That is what is happening here. Okay, so the scatter plot is telling us that in fact there is a the scatter plot is very nice. It is telling us that these variables are really linearly connected, as you can see here. All right. So this is what you do. And then the regression line itself is here. This thing that I'm trying to highlight. That is the regression line, which is what I copied over here. Let me just move this thing down a bit. So we have negative 173.5134 plus 4.8274 x. So this is the equation of the line that we're really desperately looking for. It comes up on the calculator. And what's the slope, by the way? The slope is the number before x. So the slope is 4.8274. What does it mean? It means that on average, anytime Amelia practices an extra hour from wherever she's performing, if she continues to practice 1 extra hour, the number of points is expected to go up by almost 5 points. Why is it going up? Because of the positive sign here, meaning that the slope is positive. Okay. Now you can now do a little bit of prediction. If Amelia, if somebody, oh, this is not Amelia actually. This is not about this is about the third exam score. I'm sorry, the third exam score and the final examination. Now I misinterpreted it. This is not Amelia anymore. It's about this data set over here. X is the score on the third test. Y is the score on the final exam. So because of that equation, if somebody scored 72 on the third exam score, we can predict how many points that person is going to make on the final examination. You know why? Because now we replace this X with that 72 or whatever the number is. So here I am, negative 173.5 or that plus 4.874 times 72, and you simplify. So you end up with 174.05 and so on. You are saying that you are predicting a score of 175 points out of 200. Should somebody score 72 points out of 80 on the third exam score? Remember, these are out of 80 and the Y values are out of 200. That is what we have over here. All right. So we are now saying something. Okay. So that is the preliminary of what we call the regression equation. Yes, we can recover that equation using calculus and algebra, but the calculator takes over the heavy lifting for you. You do not have to do anything. Okay, let's continue the analysis of this slide. There is something called the correlation coefficient. So besides looking at the scatter plot and seeing that the line seems reasonable, how can you tell if the line is a good predictor? Yeah, we are saying here that we are using the score on the final, on the third score, the third exam, to predict how somebody is going to perform on the final examination. But how good is that prediction? How good is the score on the third test? A good predictor. How good is it a predictor for the results on the final exam? We use something called the correlation coefficient, which is another indicator of the strength of the relationship between X and Y. We call it the correlation coefficient. It is labeled using little r, okay, which is a numerical value which provides a measure of strength and direction of linear association between X and Y. If I take you back to my picture here, you will see that among the outputs from that data, look at the very first one here. It says the correlation coefficient, R, is equal to 0.6631. So that is a strength. That is a measure of how strong the linear connection between the two variables is. Let us say something about that value R. By the way, the properties of that number R is that it must always be between negative and positive 1. Never is it ever gonna be after 1 or less than negative 1. The size of this number R indicates the strength of linear relationship between X and Y. Values which are close to negative 1 or close to positive 1 indicate stronger linear relationship between X and Y. So in other words, if the value is very, very close to negative 1, then you are saying that the values are really almost on a straight line which is going down. They are jammed together, fitting almost a perfect line. When the values are very close to positive 1, then you are saying that they're almost fitting a line which is going upward, which is increasing. So the stronger, the closer the values are to negative 1 or positive 1, the greater the strength of the linear relationship between X and Y. If R is 0, then there is no linear relationship. If R is very, very small, if R is 0.05, then you can quit that project because you're saying there is no indication of a linear relationship. It doesn't mean that there's no relationship. We are saying linear relationship. If R is 1, that's the perfect positive correlation. If R is negative 1, that's the perfect negative correlation. In other words, they are really fitting a straight line going up or a straight line going down. A positive value of R means that when X increases, Y tends to increase. And when X decreases, Y also tends to decrease. That's what we call positive correlation. A negative value of R means that when X increases, Y tends to decrease, and when X decreases, Y tends to increase, so-called negative correlation. And here's something very interesting. The sign of R, it can be positive or negative, right? The sign of R is the same as the sign of the slope. Yeah, so somehow when the slope is positive and you end up with a correlation coefficient which is negative, there's a problem. They go in the same direction. They are either both positive or negative. So, among the concepts, you have to know that, that's how they work together. If they give you a collection of possibilities, if you know that the correlation, the slope is positive, then ignore all the correlation coefficients that are negative because both of them should be in the same sign. All right. So again, this is a positive correlation. This is a negative correlation. This is zero correlation. Now, here's something. This is also very, very important. What does it mean? Correlation does not imply causation. In other words, the Y values are not going to do what they do because of X values. The data just tells you that the two variables are correlated. They are maybe positively correlated, but one is not causing the other to be what it is. Let me give an example. Some time back in Florida, I think a couple of years ago, there was a positive correlation. There was a positive correlation between number of gallons of ice creams number of gallons of ice cream eaten, and the number of drownings, number of people drowning, number of people drowning during one summer. During one summer. What am I saying? During the summer of that year, when summer began during that year from June all the way through September, they noted that the number of gallons of ice cream was a good predictor of how many people are going to die during the summer. So as the number of gallons of ice cream eaten increased, so did the number of drownings. People drowned in the oceans, in the lakes, in the rivers, and whatever. But you know what? This did not mean that people are drowning because they are eating ice cream. There was just a positive correlation. We could not say that eating ice cream was responsible for people drowning. Matter of fact, some people who drowned never even ate ice cream. That's the funny part about it. Some people who drowned in the lakes not even eat ice cream. Turns out that there was an underlying reason for that. The heat. Because of the heat, many people bought ice cream to cool off, and many people also jumped into the oceans, in the waterways, to try and cool off as well. But there was a positive correlation. So correlation, there was no causation. So make sure you put that in your bag. So that is what we call the correlation coefficient. There is also something else called the coefficient of determination, which is labeled as R squared. Let me again go back to my picture. You see, after the correlation coefficient, there is the coefficient of determination. That coefficient of determination is the square of the correlation coefficient. Okay. R squared, that value, is many cases expressed as a percentage. And it can be explained, it represents the percent of the variation in the dependent variable y that can be explained by the variation in the independent variable using that line. In other words, let me go back to my line over here, which we have, right? Which we have as, the regression equation right here, negative 173.51 plus 4.83x, where the R square is 0.4397, which we can change as a percentage, right? What this is saying is that the changes in the score on the final examination is response, the changes in the third exam, 43% of the changes in the final examination is attributed to the way the third exam is, the way the final exam is changing. Let me repeat. It tells you what percentage of the variation in the y variable is accounted for by the variation in the x variable. So approximately 44% of the variation in the final examination can be explained by the variation in the grades on the third exam. So how you perform on your third exam accounts for about 44% of the changes in how you're going to perform on the final examination, which is a big deal. So that tells you how important the third exam is. The bigger this number is, the better that variable is a predictor. How about the remainder? Well, I'm putting it right here. 1 minus R squared is the percentage of the variation that is not explained by the variation index variable. So in other words, 56%, because 1 minus 44%, 56%. 56% is maybe attributable to maybe lack of sleep, which we didn't quantify. Maybe you're not feeling well. Maybe you didn't have your internet running well. Maybe. So other reasons why you performed the way you performed on the final examination are attributing to 56%, which we don't know right now. These are unexplained, we don't know. But 44% for sure is because of the way you performed on the third examination. That's a big deal too. How do we find it? We square the correlation coefficient. But the good news again is that once you enter your data in the calculator like we did here, everything that you need comes up on the same screen. So right now we've seen a bunch of things. We can enter data on the calculator very carefully. I'm going to explain to you what the meaning of, in fact, you've seen this before. This is like a test of hypothesis. We're going to see that. But above all, the scatter plot comes up. The line of best fit also is shown. And the correlation coefficient comes up, just as the coefficient of determination comes up. By the way, the equation of the line comes up. And of course, we know what p-value is. We're going to look at it as well. So it's a one-stop area. Everything that you need comes up on that calculator. Okay. So now that we've at least seen how to create the regression line, how to look for correlation coefficient, how to go for the coefficient of determination, let us now go look at the last part of the puzzle. What does this mean? There's a test of hypothesis. The p-value comes up, and this is for testing the significance of the correlation coefficient. In other words, how sure are you? Let me go back. If I look at this data here, this line here came up because of that data. What if I collected another data set of 11 people? 11 people who did both the third and final examination. Could I get close to the same information? How significant is this linear regression equation in particular? How significant is the correlation coefficient? Because the correlation coefficient gives us the strength of the linear connection. How significant is, how reliable is. In statistics, we always look for reliability. That is why we test a hypothesis. So this is the last part we're going to see here regarding this chapter 12. And I'm saying here that the correlation coefficient tells us about the strength and the direction of the linear relationship between X and Y. However, the reliability of the linear model also depends on how many observed data are in the sample. We need to look at both the value of the correlation coefficient R and the sample size together. So we perform a hypothesis test on the significance of correlation coefficient to decide whether the linear relationship in the sample is strong enough to use for model and to use to model the relationship in the population. Remember, this is come from a sample. Can we use it in place of the population? That is the significance we're talking about. Test a hypothesis. All right. So essentially, here's the thing. Little r represents the sample correlation coefficient. Rho represents the population correlation coefficient, which we don't know. So we are going to test a hypothesis on rho, the population correlation coefficient. So in other words, yes, you have your little r on this in the sample, but you are going to test a hypothesis on the bigger picture. And so we are going to create a test of hypothesis. And when we talk of a test of hypothesis, we're gonna look for the p-value. We compare the p-value with the level of significance, and we make our decision accordingly, just like we did before. So if the test concludes that the correlation coefficient is significantly different from 0, what does that mean? In other words, we have a bunch of things here. The null hypothesis is always that rho is equal to 0. In other words, you assume that there is no connection between X and Y. And the alternatives are going to be few of them. Rho less than 0, rho bigger than 0, or rho not equal to 0, just like we did in chapter 9 and 10. So it's going to be one of the three. But the null hypothesis, in the null hypothesis, you always assume that there is no linear connection. I mean, that's the status quo. Somebody has to prove for us otherwise that indeed there is a connection between X and Y. All right. So if the test concludes that the correlation coefficient is significantly different from 0, we say that the correlation coefficient is significant. In other words, that data is for real. And the conclusion is there's sufficient evidence to conclude that there's a significant linear relationship between X and Y because the correlation coefficient is significantly different from 0. In other words, there is a significant linear relationship. We can use the regression line to model the linear relationship between X and Y in the population. If the test concludes that the coefficient is not significantly different from 0, in other words, it is close to 0, we say the correlation coefficient is not significant. So there is insufficient evidence to conclude that there's a significant linear relationship between X and Y. There is not a significant linear model, so we cannot use the regression line to model the population linearly. That is what is happening here. All right. So again, the null hypothesis is always that the alternative can be few of them, rho less than 0, or it can be rho bigger than 0, and you take it as well. So if I just go back to my calculator, that is why up here next to our data set here, the null hypothesis doesn't change. The onus is on you to determine which of these three options is your alternative hypothesis. And definitely the p-value is over there. The rest, you know what to do. You pick the p-value. You compare the p-value with alpha. Alpha must always be given to you, and you take a decision. If the p-value is low, the null must go. If the p-value is high, the null must fly. It doesn't change regardless. All right? Okay. So technology does it already. I don't have even to go through all this. You know, pretty much you've seen what I did before. You go in there, and the big deal is to be able to conclude when you reject the null hypothesis. When you reject the null hypothesis, which is assuming that there's no correlation, then you are saying there is sufficient evidence to conclude that there is a significant linear relationship between X and Y. If you do not reject the null hypothesis, there is insufficient evidence to assume that there is a linear connection. You are saying, you know what, you have this data set, but this data is not significant enough to prove the existence of a linear relationship between X and Y. There is simply no evidence so far. Okay, so let's look at this example. I think we have the same thing here. You know, we have the same thing that we had over here. And if I check out my thing, the p-value is right here. So imagine if you had entered the data like we did here, the p-value is 0.026, 0.026. And if we let alpha be 0.05, definitely this is less than alpha. We reject the null hypothesis, meaning that there is a significant linear relationship between X and Y. So in other words, it's okay to use the performance on the third exam score to predict how many points somebody is going to make on the final examination, as you can see here. And then things move on. If we had not rejected the null hypothesis, then as a researcher, you'd have maybe to get another data set and maybe change the method of collection of your data to again, and you test it one more time to see what is happening, right? All right. So basically, after having this on the same example, suppose you want to estimate or predict the mean final exam score of statistics students who scored 73 on the third exam. The exam score is 65, 75. The smallest value is 65, the highest value is 75. Since 73 is between the values of 65 and 75, it is okay to substitute 73 into the equation. After all, we rejected the notion that there is no linear connection. So there is linear connection. So it's okay to predict. So when I plug in 73, yes, somebody who scores 73 on the third exam out of 80 is expected to score 179 out of 200 on the final exam. Would you predict the final? What would you predict the final exam score to be for somebody who scored 66? Again, you plug in 66. I didn't work on it. Let me try to do that. So if I grab negative 173, no, just a second. It is 4.83 times 66. And this is 173.51. 145, 145.27. So if somebody scores a 66, you are predicting that person's final exam score to be 145 out of 200. What would you predict the final exam score to be for somebody who scores a 90? Now check this out. 90 is outside the range. You cannot extrapolate. It is not permissible to predict outside the range of X values, because the linearity, the equation could have changed by then. So when the value of X is outside the domain that you've been given, you do not predict as such, okay? The consumer price index is the average change time in the prices paid by urban consumers for consumer goods and services. It affects nearly all Americans because of the many ways it is used. One of its biggest uses is a measure of inflation by providing information about price changes in the nation's economy to the government, business, and labor. This CPI helps them to make economic decisions. The President, Congress, and the Federal Reserve Board use it to formulate monetary and fiscal policies. So here is the table. X is there. Y is the consumer price index. All right. So if you put in these guys in the calculator, you can, now you know what to do. You put those guys in the calculator, and all this can be answered by typing the guys in the calculator. So here's our, when I did so, this is the equation, negative 32.04 plus that, okay. Find the correlation coefficient. I think the correlation coefficient was 0.86, which is pretty high. And you know what? The p-value was very, very, very small, which is less than alpha. So what does that mean? It is significant. So it is a good thing to use the years as a predictor for the consumer price index. The following table shows economic development measured in per capita income. Let me see if I can. Per capita income. So then you have the year, then per capita income, per capita income. Again, you can enter the values. You want to make sure that you do it in 2 columns. You enter all the years and the subsequent values as well, right? And then what are the independent and dependent variables? The independent variable is the year. This is the X. It's the same X and Y put in 2 columns. So the independent variable is the year. The dependent variable is the per capita income. When it says do a scatter plot, you can always do that. Use regression to find the line of best fit. It was this guy here. Interpret the significance of the correlation coefficient. Well, the p-value, by the way, the correlation coefficient is 0.64. As you can see, it is very close to 0. The p-value was very large, bigger than alpha. Any alpha you can pick. So we do not reject the null hypothesis. In other words, the correlation is not, isn't significant. The correlation is not significant. Yeah, and pretty much when this happens, the rest of the questions here really are not shows. Once there's insignificance, who cares about the rest? You know, the rest really don't matter that much. Let me see what I did over here. F. What is F? Find the coefficient of determination and interpret it. Well, the coefficient of determination is the square of R. So if I square, you get 0.0041, which is less than 1%, meaning that, yeah, the X variable is not a good predictor because you are saying that the variation in the per capita income only less than 1% is explained by the year. So you cannot rely on the years to predict the per capita income. What's the slope? The slope is the number before X. So the slope is 0.068. What does it mean? Because it says use the line of what is the slope and what does it mean? It means for every increment of 1 year, each year that increases, you expect the per capita income to increase by a decimal 0.068, whatever the units are. So it's really not a very good one, but the bottom line is you gotta know how to put your data in the calculator. You gotta know how to make the interpretations, look at the p-value, and you take it from there. So at this point, I'd like to go through some examples in the homework and we check it out from there. So when I go to chapter 12, there are just 2 sets of homeworks. One of them is about the concepts, the linear regression concepts, and the other one is really to test significance of the correlation coefficient. So let me go for the concepts here. And we check out what is going on here. So then if you need it, we have the calculator right there. The link comes up. And now the first question is asking for the correlation coefficient. So when I copy this guy, they want the correlation coefficient to 4 decimal places, right? So there it is. And let me first reset this calculator. Now, here's what I was saying. Excuse me. You can copy this guy. Let me try it. You can copy these values from the homework and paste them in this area right here, Control V. And as you can see, the data set is really okay. Now, this thing, you know, if you just press calculate, it's gonna cry. It's gonna tell you, please select an alternative hypothesis. In this case, it doesn't matter which one I pick. All I need is to find the correlation coefficient. Let me just pick anything here. And when I do that, it is negative. As you can see, the points are going downwards. And, you know, the correlation coefficient is right there, negative 0.8948. Negative, oops, come on, sorry. It is negative 0.4, 0.8948. 0.898. That is our correction coefficient. Let us see whether we are good on that. 8948 it is. So that's that easy. Okay. All right, look at number 3. Oh, come on, sorry. Just make here is number 3. A researcher wishes to examine the relationship between years of schooling completed and the number of pregnancies in young women. Our research discovers a linear relationship, and the least square regression line is right here, where X is the number of years of schooling completed and Y is the number of pregnancies. The slope of the regression line can be interpreted in the following way. By the way, the slope is -3. The slope is not 5. The number before X, whether it is before or after, I don't care. The number that is before X, the so-called coefficient of X. The coefficient of X. So let me see. When the amount of schooling increases by 1 year, the number of pregnancies tends to decrease by 3. And that is it, right on the money. Look at the second one. When the amount of schooling increases by 1, the number of pregnancies tends to increase. No, this is not increase, that's decrease. When the amount of schooling increases by 1 year, the number of pregnancies tends to increase by 5. No, that 5 is the y-intercept. The slope is the coefficient of X in the equation that you get. Okay. Now let's see. Look at these scatter plots here. Match each scatter plot shown below with the one of the 4 specified correlations. So if I look at this guy, these are 4 of them. There are 2 negatives and 2 positives. So if I look at these scatter plots, it is evident that the first one and the third one are going to be positive because of the pattern. The second and the fourth are going to be negative because they're going down. Now, when I look at the 2 positive numbers, one of them is 0.71, the other is 0.50. This scatter plot is the one which appears to be closer to being on a straight line. They are closer together than the first one to me. That's what I think. So I think this is going to be 0, which is part D. And this should be part C. And then, by the same argument, these 2 and 4 are negative. This is more negative than the other. So this should be closer to -1. So that should be -92, which is B. So this should be a B. And this should be the A, the very, very first one. That's what they're talking about. So you look at the direction of the scatter plot and you use it to concoct something out of what is going on. 6. Let me pick 6. Let me pick number 6. All right. Choose the most appropriate to complete the sentence in order to indicate a strong correlation between variables. The correlation coefficient must be near -1 or +1. That is it, a strong correlation, either below, next to -1 or next to +1. That's what I talked about, okay? We have statistics students in Oxford College sampled 9 textbooks in the Conda bookstore and recorded the number of pages in each textbook. The bivariate data is shown below. They want us to create a linear equation here. Let me see which one is better. Doesn't matter. Okay, let me pick number 7. And number 8, you can try on your own. So here is number 7. They want us to determine the linear model. So what I'm going to do is to come here and copy. I'm gonna copy. Don't copy the headers. It is meaningless to copy the headers. So when I copy this guy, I reset him, everything goes, and I paste over there. I can, at this point, set anything. Setting it left or right doesn't matter. The correlation coefficient does not depend on the direction of the alternative hypothesis. They want us to find the regression equation. So here it is. Now you have to be very careful here. And that is why you need to put a meaning. Here is the equation, 16 plus 0.3354 plus 0.1391x. But the way they want it here, they're saying y is equal to something x. So whatever is before x must be what you put here. So let me go back to my problem. So whatever is below x, by the way, 2 decimal places, I'm gonna write 0.14. Oh gosh. 0.14x plus 16.34. 16.34. 16.34. Use the model to estimate the cost when the number of pages is 229. 229 is, what is 229? 229. This is unusual because 229 is outside. I'm surprised they're gonna use it because 229 happens to be way below 275. But I guess the author did not think about that, so let's just do that anyways. So 0.14 times 229, okay? And then we add 16.34 to give us 48.4. But I'm surprised, let me just check it and see whether. Ordinarily, that number would be way too below. Let me go. Let me see what we have here. 0.14, 16.34, and 48.4. Ordinarily, that number would be impossible because it is very far, but I guess that passed. So when you copy, even this can be copied, whether it is, with the calculator, just to show you what I'm talking about. If you were looking at this example here and you copy, oh, you want to be careful here. Oh, you're going to move the Y. Okay. So when I copy this, if I'm lazy, if you are lazy like I am, and you wanna just use this thing, I am going to remove this Y here. Let me see. 11. Let's be very, very careful. You have to be, you have to modify, you have to modify it, buddy, because now here's what will happen. 11, 6, 8, 1, 7, 1. Let me do this. I'm glad this came up. You have to modify it. 8, 1. In fact, I can just do this. A small space. Put a small space. Put a small space. Then 2.7. You see? And then remove this. And put this over there. And then you want to remove this Y here. This Y is meaningless. 13.7, 10.8, 10.1, 7.3, 6.5, 6, another 6, and 4.5, So this one could not fit on the other line. So we leave it aside. I think that is it now. You see? So when I say calculate, I get my line. And the value of R, let me see, you can answer everything you want to do. But, so whether the numbers are going horizontally in a horizontal fashion or as rows or as columns, it doesn't matter. If you had entered them as columns, you would get the same answer as well, okay? Okay, let me see, maybe one more here. Let me pick number 11. Let me pick number 11 here. It says the equation of the regression line for the day's high temperature X and the mean number of robberies committed that day is Y hat equals 0.3x plus 28. Then, on average, days with the higher temperatures also tend to be days with a greater number of robberies. Yeah, because the slope is positive. That is true. Or the slope is positive, Let me pick another one. Let's look at number, excuse me, number 12 as before we move on to the next two. If the correlation is 0, then there is no relationship between the two variables. That's not true. When the correlation coefficient is 0, it is telling you that there is no linear relationship. There could be some other relationship. What you are removing here is the linear relation. There is no linear the word linear is very important. All right. Okay, so let me now look at the other part of the homework, which contains testing the hypothesis, which is right here, testing for the correlation, which is linear regression. Yes, we have it's the same calculator anyways. So let me go to number 2 here. So we are back to the same kind of stuff anyways, right? Like what we did before when we're testing hypothesis. When the P value is low, the null must go. When the P value is high, the null must fly. It's the same old thing. Conclusion, all that. Okay. We have the conclusion is also very important. This is one of the reasons why you are even doing what you are doing. Okay. The data shown below consists of the price in dollars of 7 events at a local venue and the number of people who attended. Determine if there is significant negative linear correlation. So the wording tells you that in the alternative hypothesis down here, rho is less than 0. The null hypothesis is always rho equal to 0. Okay, so determine if there's a significant linear correlation between ticket price and number of attendees. Use a significance level of 0.05 and round all values to 4 decimal places. So number 1, they want the linear correlation coefficient, okay? So I'm gonna copy, let me copy this stuff. No. Copy. So when they're in column fashion, you can afford to ignore the the headers, because the heading is not necessary. So I have it very quickly. I paste it right there. Okay. Then this is why this part is here. The alternative hypothesis is less. I'm gonna pick that up. And then calculate. So among other things, you want to know the correlation coefficient to 4 decimal places. How about negative 0.8683? Negative 0.8683. What's the p-value? Okay, the p-value is 0012. 0.002. And the level of significance, by the way, is 0.05. So this guy is less. And if it is less, what do? The null must go. You reject the null hypothesis. What's the conclusion? There is sufficient evidence. In other words, there is a significant negative linear correlation between the ticket price and attendance. That is it. There is a significant negative. How do I know it is negative?
Well, I'm the only person in this bitch, always.
How do you know it is negative? Because it is right here. Because in the alternative hypothesis, it is right here, less than. So there is a significant negative correlation coefficient between the ticket price and attendance. And that's the end of the story for this problem. So we entered our data in the calculator. And the good thing is you can copy and paste. You can just copy the data set like I did, copy it from here, and I pasted it in the calculator right here. And everything just comes up like it's supposed to. and you are out of there. Okay, let me pick another example. Let me go back here. Okay, let me pick this one here. Okay, let me pick number 3. Let me cut number 3 and paste it in our chat area. All right. All right. Let me copy up to E here. Okay, and then there's something more. F, it goes all the way. So this is a complete question, matter of fact. Okay, up to H, then after H, there is I. So this is a very, very complete problem. It really is a total package for everything. All right, so let's look at it now. I copied it. So let's go over here. It says, what is the relationship between the attendance at a major league ball game and the total number of runs scored? Attendance figures in thousands and the runs scored for 8 randomly selected games are shown below. So this is attendance here. These are the runs. Now, here's what you can do. If I bring up my calculator here, I first reset it. You can enter them either in row form or in column form. What do I mean? You can enter 37 space 50 space 37 all the way and come for the second row. Or if you are lazy like I am, I can go to the original problem and I copy and paste. I can copy these guys, but be mindful of the fact that something else comes up, which you must, I mean, these runs, you don't want those runs to be there. Even, okay, let me do this. If you did this, you could even just copy and remove those headers, right? Maybe that's better. If I bring that data that I copied and I put it here, then all I have to do is to edit it very well. Remove the headers. So this is a tendency, and I want to just keep one space. That's okay. All right. Then 44, 12, 60. That is true. And who? 20. Yeah. And then remove the header also for the runs. Just clean this up. I want to do that. I prefer to use one space. The number of spaces doesn't matter. I mean, you can, I just want to make sure that it is one just for readability purposes, but it doesn't matter. I prefer to just have a space of one. You must put a space there or comma if you want to use commas. All right. And then find the correlation coefficient. By the way, this is a two-tailed test. So I'm going to pick the two-tailed test right there. Then bring up my stuff here. Calculate. So the first thing I want to get is the R value. What is R? 0.8771. 0.8771. Okay, what's the p-value? 0.042. 0.00. By the way, you really want to make sure that the alternative hypothesis that you select is the right one. So in this case, The reason it is this gonna be you. In fact, let me go back here. You have to select row here. This is row equal to 0, and then row not equal to 0. So this is row here equal to 0, and row not equal to 0. So this wasn't a left tail or right tail. And by the way, the reason I know it is not left or right is look at the problem. What is the relationship between a tendency and the total number of runs? That is it. So because it was blunt, it wasn't very specific as to whether it should go left or right. Unlike this example here, if I go back to this previous example, determine if there's a significant negative. That is very blunt, negative. And that's why the null alternative hypothesis is a left tail, but not this time. It wasn't very specific. They just want to know if there is a relationship between the two variables. So we go for the two-tailed test. Use the level of significance to state the conclusion of the hypothesis test. In the context of the problem, remember now the p-value is less. So we reject, by the way, right? We reject the null hypothesis because p-value is less than alpha. Because the alpha is what? 0.05 right here. All right. So because of that, there is significant evidence to conclude that there is a correlation. You have to be very, very careful. So this one I throw away. Now the race is between 2, 3, and 4. Look at 2. It says there is a statistically significant evidence to conclude that a game with a higher attendance will have fewer. How do you know? This would be true if we had a one tail, maybe left or right. There is significant evidence to conclude that a game with a higher, we don't know. So we just have to be blunt also. There is evidence to conclude that there is a correlation. That is the best we can say. If the alternative hypothesis had been one-tailed, the answer would be one of these, depending on whether it is left or right. But this is a two-tailed test. We are saying there is a correlation. What is R square? Yes, 7692. Oh, two decimal places, 0.77. Interpret R squared. You can say that, you know what, there's a large variation in the run squad in the baseball games, but if you only look at games with a fixed tendency, the variation on average is reduced by 77%. Yeah, this is it. This is the best description because you are saying the variation that is accounted for by the X variable. It is not telling you that chance, this is not about the probability of attending a game or whatever it is. No, you are saying that the variation that is accounted for by the attendance is 77%, which is the same as saying the variation is reduced by that much. The equation now, two decimal places, okay. The equation is, what is it? 3.57. You see now the X is to the right, you know, so you have to be very, very careful. 3.57 plus 0.13 X 0.3. Use the model to predict the runs scored at a game that has 22,000 people. Now we're gonna be careful. These are already in thousands. So just plug in 22. So you grab 3.57 plus 0.3 times 22. You grab your calculator and you 3.57, 6.43 to the nearest whole number, 6. Let me see, right? Yeah, I think if you talk of 22, I mean, 12, 22 is also 6, 20, yeah, so that's okay. Interpret the slope. What is the slope? The slope is 0.13 right here. For every additional 1,000 people who attend the game, there tends to be an average increase of 0.13 runs per game. That is it. Yeah. Interpret the y-intercept in the context of the problem. Now, let me write this thing here. The equation is y equal to 3.57 plus 0.13. And this guy is y-intercept. Now, what would it mean? The y-intercept is the value of y when x is 0. This is the value of y when x is 0. Now, but let's see whether it makes sense. You are saying that when there's no, when nobody is attending, when nobody is in attendance, they're gonna be scoring 3.57, which is like 4 runs. So it is part D, the last one here. So you are now saying that the best prediction for a game with nobody in attendance is that there will be a 4 run squad. 3.57 is almost 4. This is almost 4. That is what we're talking about. All right, let me see if we are okay. Maybe we can stop or try one more example and we leave it at that. Let me see, just to make sure we are good. Is this the one? Yeah. 0.89. Oh, they want 2 decimal. Oh, come on, I messed up. 2 decimal places. How come I get 29? I think I made a mistake, right? 0. Oh, no, this is not the one. I think, is this the one? Which one is it? Yeah, this is the one. I was going for a different one. 0.89. I missed. This is 2 decimal places. This should be 0.88. I read my instructions very carefully. All right. And if that is 0.88, of course, this is going to be a rho equal to 0, rho not equal to 0. The p-value is 0.042. Yes, it is 0.042. And part C, there is statistically significant evidence to conclude that there is a correlation between attendance and runs scored. The R square is going to be 77. I think that's what we got here. And the meaning of that is that, yes, there's a large variation in the run squad in the baseball games. But if you want to look at games with a fixed attendance, this variation on average is reduced by 77%, is accounted for by 77%, all right? And the equation here is y 3.57 plus 0.13x. I guess that's what we had here. Yep, right there. And what is it? Use the model to predict. So we're gonna get like 6 of them, 6 runs. When we plugged in here, we got a 6. And H, for every additional 1,000 people who attend the game, there is an average increase by 0.1 and so on. The best prediction for a game with 0 attendance is that there are going to be 4 runs scored. So the y-intercept is that number, and the meaning of the y-intercept is the value of y when x is 0. Let's look at one more example and we stop. So the rest you can check out later. I can, let me take the same thing here. Okay, let me go for the very last one. The very, very last one. This is C and D are a square so let me copy E, F, and G. E, F, and G. All right. All right. And then there is H and I. Okay. H and I. So once you get the hang of it, for any of them, it is really the whole business revisited. The grocery store manager did a study to look at the relationship between amount of time in minutes customers spend at the store and the amount of money in dollars they spend. And this is the data. So again, we have to enter that data in the calculator. Again, I don't wanna go through that stuff, but copy. I'm gonna copy. And then I remove the headers. It is better. So when I come over here, I reset and I copy. Then I would like to manage it somewhat. So the time, okay, 8:24:07. Again, you don't have to remove the spaces. I prefer to remove them for readability purposes. I wanna have them to be separated by just one space up to 10. See, now that's the first row, which really is very well formatted. Then I move the header here. As far as the money is concerned, remove that, keep the 68, 45, 63. There it is. So I have my data now in 2 rows. Again, there can be either 2 rows or 2 columns. I'm going to go for the alternative hypothesis and I do the calculation one more time. R to how many 2 decimal places? 0.85. 0.8. So this is 0.85. And this is rho equal to 0 again. this is rho not equal to 0, the p-value 0038, there is significant evidence to conclude that there is a correlation. Yeah, that there is a correlation, that is it. And the R square is 72, 0.72, two decimal places. There is a large variation in the amount of money that customers spend at the store, but if you look at the customers who spend a fixed amount of time at the store, this variation is reduced on average by 72%. What's the equation? The equation is 15.24 plus 2.77 x, because I changed to two decimal places as needed. And we can use the model to get 18 people. So 15.24 plus 2.77 times 18. You grab your calculator. 15.24, and you end up with 65.1. It's gonna be 65 people. $65 rather, not people. $65 is what you predict. Somebody spending in the store, spending 18 minutes in the store, is expected to spend $65. What's the slope? Positive 2.77. For each additional minute the customer spends in the store, the customer is gonna tend to spend $2.77 more. The y-intercept, let me see, what's the y-intercept? The y-intercept is right here. Meaning that if somebody spends no time in the store, then, but how can that happen? If the customer spends no time in the store, I don't think that has a practical interpretation, meaning, I mean, how can you spend 0 time in the store and spend money? Is it online or something? Maybe, but for now, then we shall see when we check it out, but I'm tempted to go for that because, you know, if you spend no time in the store, how can you spend, I don't know, let me check. Let me check to see what is going on here. So this is 85, which is good. Okay. This is row. This is 0038. Yeah, we are good. 0038 it is. There is a correlation between the R square 77, 72. We saw that. There is a large variation and so on. I want to look at this equation. 15.24 plus 2.77. Yes. Okay. Now, $65 is what you're gonna spend if you spend 18 minutes. Every additional minute you're gonna do that is what I wanna check out. This has no practical meaning because, so in as much as the y-intercept is always that number, you have to look at the context of the problem. You cannot tell me that if you spend no time in the store, you're gonna spend that much money. That doesn't make sense. So in this case, the y-intercept has no practical meaning. So tomorrow, I'll look at the only section in chapter 13, just one section. It may take me just less than an hour, and then we are done. On Wednesday, I will go through, if possible, I may even go through I may go through the study, the review tomorrow as well. I think I may do that after chapter 13. I may go through the review tomorrow as well.